So now here is our parallel circuit. Parallel circuit. So a parallel circuit is a circuit which has two or more paths for current to flow through or for charges to flow through. Remember, the charges will be flowing from the positive side, positive terminal, to the negative terminal. Why are they flowing in this direction? Because they are attracted to the negative terminal. That's it. So because here they're being repelled, it's just positives. So there's actually an electric field around here. So they are being pushed this side and being pulled this side. And as we can see, the charges are able to take this part. They're able to take this part, and there is also this part, right? So supposing now the reading for ammeter 1 is, say, for argument's sake, say it's 4 amps. 4 amps, right? Is it okay to write 4? I don't like writing similar numbers because, okay, let me cancel this. Let me just cancel this, it won't work well with us. The numbers have to be different. They have to be different. Okay? They have to be different. Let's see what happens. Yes, we are good to go. Okay, I will choose 3 amps. 3 amps. 3 amps. That's the current through the ammeter 1. And what we should be aware of is the fact that the current from this positive terminal, this is the only part up to here. So the charges haven't separated, right? The current haven't split. So it's still the same route. So when we get here now at the junction, this is the junction, okay? There are 2 paths which can be followed. There is this one, and then there is this one, right? And what we know is the charge will choose the less resistive part. Okay, let's talk about humans. If you were walking in the forest, right? And then maybe, I don't know, it could be anything happening really. What can we choose as our scenario? I don't like choosing scary things, but let's just think about it. Let's say you are chased by very bad people, and you see a river, you approach a river. Can you really run along the river? Or your best bet is to cross it so that you can run on a hard surface, right? You are going to choose the part which is easier, right? And if you see that there is a lot of, maybe the grass is tall, unless you want to hide, but you want a clear ground where you can run at the top of your speed, right? Without hindrance, with less hindrance. So, charge kana current ya go chusa tsela e mothofu akere go tshwana le lona gompieko ke tikirise example ya gore go tshwana le lona gompieko ana e ka re gongwe mo sekolong, right? Go na le gate e nnyane le gate e tona, o a re tswe mo kganyetsa gate a re ko classroom, maybe there is fire go a sha akere go na le lebati e ka nna go gongwe hela, I don't know, but the issue ke gore kgoro e nngwe ne tona e nngwe ne nnyane, akere kana ke mo busing kana ke kae hela, just try to imagine something. Try to imagine something. Di-charge di tshwana le batho hela, di thusa tsela e motlhofo e je ka taboga gore yo kae ko negative terminaleng. So a gore ke mo classroomong kana ke mo busing kana ke kae kana go kerekeng, go na le mollo, go na le emergency akere mo busing go ka le gore to pagame bus la ile tsone ke sprinter ga o leba go godimo yana go na le go te emergency exit akere depending mo goreng go iragala eng kae gone mo busing eo, but let's stick to the classroom. Ha ile gore gongwe go na le sengwe se se iragalang gongwe go asha like I said, then re expecta gore bana ba bantsi ba ye go tswa kae ko kgorwaneng kana le gore ke gate ya sekolo go na le nyana go na le tona ga le gore la letelwa gore le tswe ka le ka se dikolo di tswalwa. And a ke dumele gore re ka bona e le gore yaanong lona le ile go thatagana ko gating e nyana, le thatagane hela ko go na le phata ka gating ye tona. A go iragale mo unless le na le a hidden agenda. But in the natural world, people will always choose the easy way out. So this is the same thing saying what the behavior like away. Even if you go to the supermarket, after buying whatever you went to buy and after actually putting it in your basket, what you look for is the checkout which has like few people queuing. That's what we do. We say, okay, fine, I don't want to waste my time. Let me check and see which checkout is congested and which one has less people. You try to kind of calculate, or okay, fine, this one has a full trolley, this one has just a small basket, it's just bread. So you want the fastest way out. So the same thing happens with charges. The same thing happens with current, right? So the current will always want to choose the less resistive part, the part with less friction, the part with less resistance, so to speak. Actually, it's a resistance, but I'm just trying to make you understand by saying friction, yes, but that's it. So in this case, what causes resistance or opposing the charges as they try to flow? Two resistors. In this branch, that's 2 ohms, and on this one is also 2 ohms. So the resistivity or the resistance or that which opposes their flow is identical on each branch between these 2 branches. So the current will be split equally. So the current flowing here will be 1.5 amps. And the current here, what is this really? I don't like what I see. But anyway, that's okay. The current here will be 1.5 as well, because the resistance is the same, right? So current, I don't like this thing, the way it does this. It's really, why is it doing this? Guys, let me try something different. Let me try to increase the accuracy. Okay, the accuracy is now increased. That's okay. So I1, which is the current here of 3 amps, is equal to I2. This is ammeter number 2, right? Then that's 2 plus I3 from ammeter 3, I3. So that's 3 amps is equal to 1.5 amps plus 1.5 amps. So that's it. So this is what we have here. So the important thing that you need to understand is because the current here at this point is 3, and then they branch, the current splits, okay? And then at this point here, this junction, they recombine, becomes 3. Yes, it doesn't have any voltage, the charges don't have any voltage, but their number is still 3. I told you the charges are just like, they are actually particles, so they can't just disappear, they can't get used up, right? So it's just like you maybe and your brother or sister, you go to the shops, and when you get to the mall, maybe you decide to go to a particular supermarket, and your brother decides to go to a restaurant, maybe to buy some fries or fried chicken or anything. Yes, after buying, you have to come together and go back home. You can't just vanish in a shop. By the same token, charges cannot disappear, or the current can't disappear around the circuit. It has to go back to the source, right? If it doesn't have enough energy to leave this terminal, positive terminal, that's okay. It will just remain here. There is nothing that is pushing it, because voltage is actually like, the source voltage is like pushing the charges to go around the circuit. This side, they are being pulled. So if that push and pull is no longer there, because it's caused by the electric field. If the electric field is too weak, then charges won't go anywhere, right? That's it. So now let's look at where charges, not charges, the resistance is not the same, and see what happens. Okay, here is another example. This is I. So the current here is I. The current here is I1. The current here is I2. So we want the value for I1 and I2. So here is the thing. As we can see, this is the positive terminal. This is the negative terminal. Current flow, positive to negative, right? So one thing that before we jump into conclusions, let's look at our circuit. This is the background thinking. This one we know is 3 amps, right? So the 3 amps up to this point, the current will split, the charges will separate, the charges will be recombining at this point as they travel upwards to the negative terminal, right? You have to listen attentively. This is what you should always be thinking about when you look at a circuit like this. So here's the thing. Current kind of sees what is happening. Like I said, when we're looking at this circuit, yes, we see that the difficulty here is less than the difficulty on this branch below. So this difficulty of 6 ohms, or the resistance of 6 ohms, is double this one on the first branch on top. So what is going to happen is current is going to split in such a way that the current here is double the current here. Why? Because, okay, we can just, from the word go, we can write an upwards arrow like this. What does it mean? It means more current, right? You have to do this when you're solving such problem. So on this branch, the current will be less. There is no way to write less, but you can write less here and here more current, less current before you do anything. Why are you doing that? Because current will choose the branch with less resistance. So what am I trying to say? I am saying more current will flow on this branch, on this branch, on this branch with 3 ohms resist. Why? Because this resistance is less. There is less opposition to the flow of charges or flow of current. Just like what I said, ka kgang ya lebati le letona, gate e tona le gate e nyane. Ha go te tswang mo sekolong kana dikolo di tswala kana go iragala ke itse gore most of the time until le irisa gate e nyane la ke batla le gore le leteletswe gongwe dikolo di tswala kana go te tswang after exam or whatever. Re expecta gore at the end of the day be re bone bana ba le bantsi ba choositse gate e tona go na le nyane. A re se re ka inyana a gona go tswa ope teng. Ga go kwa re bona batho ba kgobokane mo gate e tona ba le bantsi ba fodile o bona hela o sa irise inyane e leng gore ga ina ope. Rena kgang ya rene re buang gore gate e tona hela yone ya go heleletsa e irisitswe ke bana ba le bantsi than e nyane. Why bana ba bantsi ba irisa gate e tona? Because go motlhofo gore ba tswe ba le bantsi e nyane la fola. Batho ba le bararo ba ke ba kgona go tsenana ba like in a way long gore ba tsena at the same time, right? But he tona ra itse gore bo 6-7 ba ka hita hela ba le bantsi ile ba ka nna ba tsena ba tabogile kana ba tswa ba tabogile. So this is what we are saying. So ba go choose tona because ga e ba kganele go tswa in a way. I get so ba kgona tswa ba le bantsi. So even the current will choose this branch because there is less resistance. Resistance it's an like opposition, like it's friction, right? So friction opposed motion. I get so there is a lot of opposition kana friction ka kwana go go 6 ohms. So more charges will use this route. So having established that, the following thing that will help us to find the correct values of current between the two branches, we are going to use the ratio of resistors. So the resistance is in this ratio 3:6. We can divide both sides by 3, right? What do we get? This is 1, this is 2. So 1 is 2. So 2 parts or 2/3 will go here through this resistor, right? 1 part will go through this resistor. So that's it. Less, as you can see, less. Less means what? The total 1 part and 2 parts, when you combine them, is 3. So the total of the ratio is 3. 1/3, 2/3. Then it will depend on the total amount of current. It's 1/3 of the total current from the source, right? Source, from the power source. In this case, that's 3. So what do we say? A1, current 1, is equal to 3, which is the total current, 3A, times, there's an arrow here going up. Like we said, it means more current, right? So more current is 2/3, 2/3. That's it. 3 into 3, 1. 3 into 3, 1. 3 cancels 3. What are we left with? 2 amps. So the current here is 2 amps. Then how about I2? What do we see at I2? Less. It's less. So we multiply by 3. 3 multiplied by a third. It's not 2/3, a third, because it's less. Over 3. 3 cancels 3. Then what do we have? That's 1 amps. That's 1 amps. See? That's 1 amps. So that's I2. And I think it is clear that I is equal to I2 plus I3. As you can see, 3 is equal to 2 plus 1. That's it. So one thing to note is from here is the total current. When the current gets here, it splits into branches. If there are 4 branches, they are going to split. The current will be splitting into 4. 4, right? You'll be splitting that into 4 parts. But here is 2, this branch and this branch. And when the current gets here, it recombines and goes to the negative terminal. So maybe sometimes you might forget the formula, but what you need to understand, supposing the ratio of resistors is 1 is to 2, right? 1 is to 2. 1 is to 2, it could be 4 ohms and 8 ohms. Even if you do it as this, it doesn't matter. But 1 is to 2 is the simplest, right? And the total current, supposing it was 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 6, 9. Yes. What you're supposed to do now is, okay, you are going to take one part and give to this. That's 1, right? 1 is the 2. Then you take 2. You give this one 1, 2. Then you add 1. You give to this. Then 1 is the 2, remember? Then you take 2. You give to this one. Then you take 1. You give to this one. Then you get 2. You give to this one 2. At the end, this resistor, not resistor, but it's actually 1 is to 2, remember? And the one that gets a lot is the smaller one, right? It is the smaller one. So it will be 3, and this one will be 6. For determining which one gets more, really, you just have to look at which resistor is high. The one with high resistance will get less. The one with less resistance will get more. Will get more current. So that's it about the current. Now let's look at we can start with voltage. Let's start with voltage. At the end, we'll look at the resistance, right? Okay, next page. Let us go to the next page. This is our next page. Well, we have, let me change the color. Yes, let's use black. Once again, it is the this is a parallel circuit. Parallel circuit, my friend. And we are to talk about voltage, right? Voltage. And I want you to pay attention because after this we are going to be solving exam questions. I don't want to be bringing my own, but we are just going to solve past exam questions. Okay, here is our circuit. Here is our circuit. Well, my friends, here is a parallel circuit. Now we are looking at voltage in a parallel circuit. Let's see how it actually works. So this is the voltage. Now this is the source voltage, that the EMF, right? It's of 20 volts, and this is the positive, this is the negative, and then we have the direction of current or the direction of charge flow. So let's think about what we said earlier on. What does this 20 volts mean? It means each and every charge leaving this positive terminal will have a voltage of 20, right? That's good. Now let's talk about two charges because there are now two branches. Well, one thing that sometimes I take for granted is the direction. Here is the direction of current or charges. So these charges, like I said earlier on, they are being pushed from this side and pulled to this side, the terminal, the negative terminal, right? Remember we said like charges repel and unlike charges attract. So positive to negative. So that's how we think about it. So their goal is to go to the negative terminal. So there is no way a charge being here and going this way again, backwards. So it's not like they do whatever they like. They are being pulled. They are under electric field, right? There is an electric force that is working. So they can't just go in the direction that they like. It's not allowed, guys. So one direction, all charges. This is, remember, this is DC, direct current. So the current is moving in the same direction, right? So let's talk about the first charge. Okay, I'm imagining a charge. So I see this resistor is 2 ohms. This one is 40 amps. I could have written a big value really, like say 400 ohms. I don't care. It will change nothing at all as far as voltage across the branches or in parallel is concerned. So here is a charge. We are talking about the first charge. So this is resistor 1. This is resistor 2. We are calling this branch number 1. We are calling this branch number 2, right? Well, we are talking about two charges. Why two charges? Because there are two branches. Some charges will go in this direction, some will go, a lot of them, right? But we are not going to be trying to find the current because I've just given like enormous values here, 400 ohms. Actually, I've changed to 400, not 40 ohms, 400 ohms, whatever value you like. So what is going to happen here is the charge. Okay, here is a charge, the first charge. How many volts does it have? because no work has been done yet. So it has how many? 20 volts. It has 20 volts at this point. And at this point, as we can see, there is no work to be done. There is no component which is going to resist the motion of the charges. So at this point, like we said earlier on, as they arrive here, all the charges should have 0 volts. But at this point, all of them, they have 20 volts. So on this part, it has 20. It uses all its voltage or the energy, right? Then at this point is 0 volts. So the voltage across here, V1, is equal to 20, right? Another charge. I'm going to change the color. Can I change to, oh, this color is okay. This color is okay. Okay, another charge. Charge number 2. Here it is. Let me just write Q2. I wish I wrote Q1 for this one, but that's okay. Charge number 2. Why am I saying charge number 2? Because definitely I know that there are some charges which will pass here and some charges will pass here. The current here and the current here. We are not concerned with how many amps. What we know is that some charges will pass here and some charges will pass here, and we are going to only talk about voltage. Here it is. Here is the charge number 2. At this point, has it used any of its energy or voltage? No, it haven't. That's 20 volts. And then there it is, passes through this resistor. Then let's talk about its energy here immediately after passing this resistor, right? Its voltage V2. No, it's not V2. What am I saying? This is wrong. It's just the potential at that point. The potential here is 20 volts. After passing this resistor, let's see what we expect. This charge will definitely go in this direction. But is there any other component that is going to use the energy of the charge? No, there isn't. So immediately after this resistor, it has to be 0. Why is it not writing now? You see what? I don't know what's wrong with this. Oh, it was on eraser. That's okay. So after this resistor, it definitely has to be 0 volts, but just before it was 20 volts. So what is the potential difference? Potential difference is equal to 20 minus 0. That is 20 volts, which is the value of V2. So V2 is 20 volts. I really hope we have understood. From this, you just have to conclude that the voltage in parallel is the same. Look at this. Source voltage, EMF, is 20. The voltage here, V1, is 20. The voltage here, V2, is 20. So the voltage is the same. Sometimes I think on your notes you'll find something like this. Something like this. You might find something like this. Then 1, 2, 3. Then, let's call it V1, V2, V3. V1 is equal to V2 is equal to V3. So the reason is what I've just demonstrated in terms of charges. So the voltage in parallel is the same. Okay, let's do another example where we have more than one resistance here and see what happens in that case. And I want to emphasize something here. Well, here is another example. We remember we are still on voltage in parallel circuits, right? So what do I see? I see we have an EMF of 20 volts, 20 volts, right? And once again, let's talk of charges. This is the positive terminal, this is the negative terminal. Direction of current, this way, then this way, and this way. We are going to talk about the first branch first, and we are going to look at the first charge. Let's call it Q1, like labeling things. I want you to pay attention, because if you don't, when we'll be solving questions, you might get lost. So I really want to take some time here, because experience tells me that a lot of students are struggling when it comes to parallel circuit, and most of the times, the problems that you are going to encounter in the exam will be that of a parallel circuit, because it is a little more challenging, so the examiners, they always want to see who is more serious, I can say that, or the one who has been serious about their schoolwork. It's not about who is intelligent or who is not. It's about the effort that you put in. Talent or natural intelligence alone won't get you anywhere. You need to put in the work. Okay, so we are talking about charge number 1. For charge number 1, let's see what happens. Charge number 1, as it leaves here, it has 20 what? 20 volts, right? There are 2 branches. Remember, we're going to talk about 2 test charges because there are 2 branches. So we are going to talk about a charge that is going to choose this part, right? At this point, it has 20 volts, and there is work to be done here, R1 and R2, right? So this charge, okay, let me tell you, this charge does not know that there is another branch here or what is happening on that branch. It doesn't know. Like I said, when you are with your brother, you go to the mall, you get inside the supermarket, maybe you have to buy sugar or whatever, and your little brother has to go to, say, a restaurant, like I said before, or a hardware or anything, right? Your young brother wouldn't know what is happening this side. He wouldn't know at all. So charge 1 doesn't know what is happening in this branch. So it has 20 volts. There is work to be done as it passes through 2 ohms. There is work to be done when it passes 4 ohms, R2, right? So this one is the same as what you call it, a series circuit, right? Is the same as a series circuit. So the 20 volts is going to be split between this one and this one. It's going to be split. Because it's going to be split, I don't have a calculator here. I'm going to change the values for the source voltage to 15. I really want to make my life. Yes, like I said, I really like making my life much easier. I don't have a calculator here, and I don't want decimal places. So at this point, charge Q1 will have 15 volts, and when it gets here, it has to be at 0 volts. So that's it. Here is my charge. It's coming. Charge 1, charge 1. When it's immediately before going through any resistor here, it will have a voltage of 15 volts. After resistor number 2, because there is no other component, it will have 0 volts. So at this point, it is at 0 volt. The potential here is 0 volts, here is 15. So because we have R1 and R2, the voltage will be split such that this one gets more, double of this one. Why? Because voltage is energy that is going to be, in this case, used to do some work as it passes through this resistor. This resistor will get warmed up, so the electrical energy is going to be changed to heat, right? Yeah, that's it. So the voltage here, if you remember how we did it when you're looking at series, you can find their ratio and do some calculation. But because I now know, I'll just write 5 volts and 10 volts. Why am I doing this? Does it look simple? Yes, because 2 is double this value, right? It's actually half of this value. This voltage is half of this value. So that's okay. That's test charge 1. Let's look at test charge number 2. So test charge number 2. Talk about charge number 2. Here it is, here it is. Test charge number 2. At this point, my test charge number 2, it has a voltage of 15, right? Up to this point is 15 volts. After this resistor, there is no any other component, so it should have, immediately after this resistor, it should have 0 volts. Here it's 16. Oh, the power is running low. Let me plug in. Yeah, that's it, right? At this point is 0 volts. Here is 15 volts. So therefore, my test charge number 2 will use all its voltage here. So the voltage across PD is 15 minus 0, that is 15. So what do we see now that we have 2 resistors here? What I wanted to make you understand is, even though we are saying the voltage in parallel is the same, what we really mean is in each branch. So here it is 15, right? On this branch again it's 15 volts. So if I can have 15 resistors, identical resistors, identical or not identical, let's start with identical. If they are identical, we mean they are the same. They will each get 1 volt in this first branch. 1 volt. But at the end, the total voltage on that branch is 15. because each charge when it comes in here is going to divide its voltage, its energy, as it tries to pass through the components. That's it. So rather than saying maybe the voltage in parallel is the same, you can try to think of as each branch has the same voltage, each branch, because each charge that goes through that branch, it only has the source voltage, right, of 15 or 20 or 80. So if there are 10 branches, each branch will have the same amount of voltage, right? That's it. The only thing maybe that will be different is the current, of course. Even the resistors can be different in those branches. Okay, now let's quickly look at the resistance. Let's look at the resistance in parallel circuit. Okay, well, parallel circuit, we are looking at resistance. So in parallel circuit, we look at the resistance, and for our objective, actually it's always two branches. So in this case, we have number 1, this one is number 2. Okay, this is how we calculate the total resistance. Let's call it RT, or equivalent resistance. It's product over sum. So this is how it's done. That's R1 times R2 divided by R1 times R2, and that is 1 R1 is 2 times 4 divided by 2 plus 4. So what do we have? Our total is, this is 6, right? 6 times, oh no, not times, it's just 6. Also, if I'm to write ohms, then I'll have to write ohms squared, and then it will cancel the square because of this one. But let me just do it this simple way. That is equal to 6 divided by 8. And what is the value? Let me get my calculator and calculate. So 6 divided by 8 is 0.75, that is ohms. That's the total resistance. Actually, even if this resistor was, say, even if it was, say, I'll just change this one, even if it was 1000 ohms, the total resistance will be always 2 or less than 2. That's it. That's how it is. Even if it was 1 million, the equivalent or the total resistance will always be less than the smallest resistor. So that's how maybe you can check if you have done the correct thing. Okay, for question number 2, let's do this. Is equal to 1 times R2 divided by R1 plus R2, right, is equal to, okay, here R1 and R2, we are talking of two resistors, but we have three resistors. One thing that we can deduce from this straight away is the fact that we have two resistors in series, so we just have to add them. Okay, 3 plus 3 is equal to 6. So this is the equivalent of this. We have to combine them. Oh, do you have some space? Yes. So we can redraw it like this. We can redraw it like this. Then we have 6 ohms. In most cases, you are going to have to simplify your circuit. We will see as we solve the past exam questions. So we have combined this as they are combined in series, because they are actually in series, but it's a parallel circuit, but the resistors themselves are in series. Okay, so what we have now is 6 times 3 divided by 6 plus 3. What do we get? 6, 12, 18, and then the sum is 9, and 18 divided by 9, that's 2. Therefore RT is equal to 2 ohms. What do we see? Once again, the total resistance is less than the smallest. In this case, they were all equal. Yes, resistance, the equivalent resistance is 2 ohms. What does it mean? It means we can replace all these resistance by a single resistor of value 2 ohms. 2 ohms. So this circuit and this one, they are the same. They are the same, except that maybe if we have a component here which requires less current, and the component which might be placed here might require more current. Like for instance, at home we have a cooker where we plug our stove, so it needs a lot of current, but for the lights they need less current, right? So there will be some resistance there and there. The resistors actually, they reduce current. Okay, yeah, that's what they do. So this is the equivalent resistance. So we have simplified. So 1 we get here, then at last we get here. So let me introduce Ohm's law, guys. We don't have much time. I don't want my videos to be this long, but it's only that I want it to be clear. So from this after this example or Ohm's law, the equation that I'm giving you, we are going straight to questions. So Ohm's law. It states that the current through a conductor, is directly proportional to voltage. Across it, and the resistor is what makes it a complete equation like this. So that's all we need to know. This is Ohm's law: voltage, current, and resistance. So voltage, you already know, is voltage in volts, current in amps, and resistance in in ohms, of course. Guys, I think this is enough. Now let's go and look at questions, exam questions. We are going to use past papers. Now that's enough with what we have for current. Yeah, let's go, guys.